So we are going to today look at rotation, only look at moment of inertia. And I will explain why this is so important. For example, if you want to calculate potential energy, what do you need? mgh. So you need the mass, you need the g, which is very easy to find. Obviously it's 9.8, but you need h. Okay, but m is something that you assume is known for an object, right? Kinetic energy, half mv square, right? Again you need m. Now the assumption is that we know mass of the particle, correct? Suppose you need to find mass of the particle. Now that's going to come everywhere, right? Because in every question you're going to have mass of the particle. But all of mechanics, mass of the particle is generally given to you. You have a block of mass 2m. In rotation questions, the equivalent of mass is moment of inertia, and unfortunately it won't be given to you. It is something that you have to find. So how important is moment of inertia? As important as mass is. Except you never had to find mass earlier, you need to find moment of inertia. Okay. Now if you take a particle, let us say, not a particle, let us take a slightly larger object, let's say something like this, and if I start to make this rotate around, so this is basically going around, so this is rotating, right? Now each particle here is moving. Now usually the way we will talk about this is to say, I have here some weird shaped object which is going around. Now it must be rotating about some axis. So let us say that this is the axis. So if that is the axis, so think of this as the axis. Now this whole thing is rotating this way or that way. Now generally when an object is rotating, and here we are talking about fixed axis, so this axis is fixed. Okay, so there is imagine that you can sometimes draw it like this, saying here is the axis, but doesn't give you an idea. It's a three-dimensional case. This actually is actually coming out. Okay, so that means this whole thing is rotating like this with omega. Is that okay? Now if this whole object is rotating with omega, then every particle on this object will have kinetic energy. What is the total kinetic energy of this object? How will you find out? It is the kinetic energy of this particle plus kinetic energy of that particle plus kinetic energy of that particle. It is the usual kinetic energy, except that every particle has a different kinetic energy. Now it may be as simple as a rod. This object may be a rod that is going around. But you see, the problem is this fellow has lesser velocity and that one has larger velocity. R omega will be the velocity, you know that, right? Now this was a straightforward case, it's just a simple rod. But now if I had something like this and it was doing this. Now remember, this one, there are all these particles that are rotating, then all those particles that are rotating, and then that fellow is the furthest away. So you will need to find out velocity for each one and add it up. Let us assume that we are able to do it. Let us see what it looks like. Basic idea is what is the kinetic energy, and sometimes we will call it kinetic energy of rotation. It is not like a special kinetic energy. This is just the regular usual kinetic energy. Okay, so now what is the kinetic energy? Let us assume that I have a particle here, m1, at a distance of r1. What velocity will it have? R1 omega. Now let us say I look at another particle here, m2. Let us say that the distance was r2. What velocity will that have? R2 omega. That is in this direction. This particle is going to have m3 and this is r3. It will have a velocity r3 omega. Now you know that for every such particle you are going to have m1, m2, m3, m4. You will have r1, r2, r3, r4, and each will have corresponding r omega. What will be the kinetic energy of m1? Half, so let me write it here, half m1 velocity square of that particle, which is what? r1 omega whole square. So that is r1 square omega square plus half m2 r2 square omega square plus half m3 r3 square omega square. Now we may be able to continue it like this with a finite number of particles. If it's an infinite number of particles, you'll have infinite such things to add. But that's not too difficult. By now I'm assuming you know how to add infinite series. So you're adding a whole bunch of things like this. Broadly, you'll probably do an integration. Okay, but at this stage, let's not worry about that. Look at what this looks like. Half is common. Omega square is common. I shouldn't be putting a bracket like that, but you understand the idea. So if I write this, I'm going to write it as half. But instead of writing it like that, I'll write half m1 r1 square plus m2 r2 square plus m3 r3 square and so on into omega square. This looks like half mv square, except it is half something into omega square. Omega is angular velocity. This is the equivalent of mass, and we call this moment of inertia. Okay, it is not just mass added up. For center of mass, usually we do m1 r1 plus m2 r2. This is m1 r1 square, so that means it is the second moment, is how we call it. Okay, so this is the moment of inertia. We will call this I. The symbol is I. So what is I? Sum m1 or mi ri square, where you're adding this from I equals 1 to all the possible particles. So over all particles. Now this looks more messy and complicated, but the reason I is important, at least for now, is because I is going to help you find kinetic energy. How important is kinetic energy? Well, if you're going to use work energy theorems to solve problems, well, without kinetic energy you can't go very far, no? In every problem, kinetic energy is going to land up. Potential energy plus kinetic energy. You can't do without this. For rotation, the kinetic energy you're talking about comes as half. So you can then say kinetic energy. This is the regular kinetic energy for an object that is rotating about a fixed axis. A rigid body rotating about a fixed axis has a kinetic energy which is half I omega square, which means I need to calculate I. But this I is little peculiar because it has both R and it has M. Mass just depends on the amount of stuff that is there. So for example, if I look at this is like a ring. If I took this and I crushed it, the mass that is going to have is the same as whatever it has now, because the number of atoms don't change. But right now the mass is sitting here. That means if I now assume that this fellow is rotating about this axis. Okay, so if this is the axis and this is going around like this, so then look at the distance of each particle. Suppose this same mass was distributed over a bigger ring. Will it have more moment of inertia or less moment of inertia? More moment of inertia. Why? Because the mass is the same, but the distances have all increased. Okay, if I basically brought this ring down and made it smaller, let us say by some magic I managed to bring it to this size. They both, let us say, have the same mass. Okay, if they had the same mass instead of sitting there is now sitting here, which means from here the distance is less. So r square is less for each mass. So moment of inertia decreases. If I took this rod and let us say it was rotating about this axis, okay, or like this, okay, whichever way, basically there's the same idea. Okay, so suppose it was rotating like this, then if I took this rod and I managed to basically hit it and make it smaller, made it this size, the whole mass basically came to this size, moment of inertia would become lesser. Mass will be the same, moment of inertia would have become lesser. If I took this rod and managed to stretch it out and I made it a double the length rod, moment of inertia would have become more, because it is something that not only depends on mass, it also depends on how the mass is distributed. It should, because you see the velocity depends on where the mass is. Plain kinetic energy depends on m and the velocity. But what is its velocity? That depends on how far away from the axis of rotation it is, right? If this was the axis of rotation, how far away from the axis of rotation you are. If you are close, that means your kinetic energy will be smaller. If you are further away, for the same mass, kinetic energy is larger. So to take that into account, I don't want to look at how far away it is. We treat this entire thing as if it is one piece. And so we calculate this quantity and call it moment of inertia I. Now it's an extremely important quantity to calculate. Later, in fact next class what we will do is we will use it to solve a lot of problems that use energy. So rotational energy and so on. Basically kinetic energy. But we will combine it with kinetic energy, potential energy, you know how to use work energy theorems, right? So we'll use all of that. If that was the only time this was getting used, it wouldn't be as useful. It turns out later that equivalent of Newton's laws for rotation will again come back with this, because mass comes in kinetic energy, but mass also comes in F equals ma. It will turn out that mass will also come in the F equal ma equivalent for rotation, which is torque is equal to I alpha. Again you will have the same I. Now without I you are now going to have trouble in two places. Calculating rotation, energy in rotation, and calculating force calculations. Equivalent of force will be torque. Torque to alpha, that will again involve I. And the third time this will land up is like, for example, when you throw a ball, it has momentum. Momentum is mass into velocity. It will turn out that there will be a similar thing here called angular momentum, which will again have an I. Okay, so I think I have scared you enough. This is extremely important. This is going to come everywhere. You don't know how to calculate moment of inertia, that is the end. Okay, you can close rotation. So let me assume that here is the axis of rotation and I have a single particle. This is not a rod, this is just a single particle going around like this. It doesn't matter whether it's going around like this or going around like that, but the axis of rotation does matter. For example, if this fellow was going around like this is not a useful axis. So moment of inertia is about, for a particle or not a particle, for a body, rigid body, but about an axis. This is about a particular axis. You change the axis, moment of inertia will change for the same object. So if I took this fellow and I ask, hey, wait a minute, what is this fellow's moment of inertia? Now it depends on which axis. If this guy was doing this, that means moment of inertia about this axis. And that is a different answer compared to moment of inertia about this axis, because about this axis, this is how it's going to rotate. About this axis, this fellow is going to have this much velocity, right, which depends on this radius. But about this axis, this fellow is going to have a lot more radius, right? So that means it will have larger velocity, therefore larger kinetic energy, this particle. So anyway, right now all we need to know is moment of inertia depends on the axis of rotation. Okay. So let me assume that this fellow is rotating about this axis. This is just the axis, this is nothing to do with a rod. Now this guy has mass m. Let us say the distance is r. What is the moment of inertia for a single particle? mr square. So this guy's moment of inertia is mr square. Okay. Now let us take another case. Let us say that I had a bunch of particles. So here is our coordinate system, x-axis, y-axis system. So I put one mass sitting here, and let us say that it has a mass of 2 kg. It's a particle of mass 2 kg. It must be a really dense particle. Okay. At this point, 2, 3, all distances are in meters. And I have another particle sitting there. Let us say this was 3 kg at a distance of, well, at a position. Now what is that position? The x-axis position must be positive. Let us say the x-axis position was 3, let us say this way it was minus 3. Okay. And then I have a third particle which is sitting here. Let us say this has mass 5 kg. And it is somewhere reasonably far away from these guys, right? So let us say that this was negative x, how much should I assume? Well, this was all 3. So let us say this was minus 4. And let's say this way it was plus 5. I've got 3 particles. Now, it doesn't mean you can calculate moment of inertia straight away. I have to tell you they are rotating about what axis. So let us say that these 3 fellows form some sort of a rigid system. That means they don't change their how far away they are from each other, and they are all rotating about this axis as the origin. So this whole thing is just going around like that. What will be the moment of inertia of this rigid system? Now, how does it become rigid if there are 3 particles? Hopefully there was a rigid massless rod connecting them, but it's massless and rigid. How does that work? I don't know, but let's assume that that's how it is, just for calculation purpose. Because if you make it massless, how will it be rigid? Right? But we'll assume that that is the case. Okay. And by the way, we'll do that a lot. So we'll assume that we have a very light rod made up of the lightest possible element. It still won't be light enough, but maybe we have a lithium rod. Okay. Lithium is quite light. So let us say somehow we managed to connect it and it was massless. And this whole thing is rotating about this axis. I'm not asking you for kinetic energy, I'm just asking you for moment of inertia. How will you calculate the moment of inertia? So you do each one. So you say mass 2 into this square plus that square, because the distance square, you want distance to the axis. What is the distance to the axis? 2 square plus 3 square. So this is 2 square plus 3 square plus m2 into this square plus that square. So 4 square plus 5 square plus m3, 3 square plus 3 square. Notice you will never get a negative number. Why? Because all these r squares will be positive and m's are generally positive, unless for some weird reason we put negative mass. Doesn't exist in nature, but it will turn out that we will want to do it. Because if you want to calculate moment of inertia of this fellow, I would like to say this is a full disk, then I'll put some negative mass in the middle to cancel out the disk. So that will be a good trick to solve problems, not in reality, but for problem solving. Okay, we will see that when we get there. But if I want to calculate this, moment of inertia is always a positive quantity. Ultimately it has to be positive, real moment of inertias. Okay, how do I calculate this? 2 times 4 plus 9, 13, plus 5 times 16 plus 25 is how much? 41, plus 3 times 9 plus 9, 18. So what is the total answer? This becomes 26 plus this is 205, right? 205 and 18 into 3, 54. How much do you get? 285. 285. What units do we get this in? Kilogram meter square. Kg meter square would be the SI unit. So I assume that all these fellows were in meters, like I told you earlier. Now this is basically individual particles, you can find the moment of inertia. About this axis, suppose I wanted to find this about this axis. Suppose this whole thing was rotating about this 2 kg mass. What will be the 2 kg's contribution? 0. But what will be this guy's contribution? It will be 5 into this distance square. Okay. By the way, if the same thing I asked you with this axis, what does the fact that this is the axis mean? This whole thing is going to rotate like that. So then you want this distance, you want that distance, and you want that distance. In fact, let me calculate this. I now calculated moment of inertia about O, and let us say this was the x-axis, this was the y-axis, and this is the z-axis. About O, z-axis. Both the axis direction matters and the point through which it goes matters. The exact axis matters. So z-axis, we calculated moment of inertia. But I can always turn around and say, no, I don't like this z-axis. Now I want it about the y-axis. Same question, I want moment of inertia about the y-axis. What will that be? what distances should I take? Distance to the axis. Okay. So what is the distance of the 5 kg to the axis? It's only the x value that matters. The 5 doesn't matter. Only this minus 4 will matter. So it will be 5 into 4 square. Is that clear? Plus, now for the 2 kg what matters? The distance 2 matters. Because that is the distance to this axis. Because if this was the axis, this 2 kg is making circles around this axis. The 5 kg is making circles around that axis. And this 3 kg is making circles like that. And hopefully they are all connected. So they are all moving together. Same omega. Okay. So otherwise this one doesn't make much sense. This is otherwise just simple mathematics, right? So today's class we are going to, it will going to sound exactly like mathematics. That's all. Mathematically can you calculate? Where is the physics in it? No physics. Why no physics? Because you are going to use this to do the physics next time. Okay. Today we are just going to focus on how to calculate moment of inertia. Okay. So 5 into 4 square, 2 into 2 square, 3 into 3 square. So this is 2 into 2 square plus 3 into 3 square. Do you see why this is 3 into 3 square? I just had numbers which unfortunately matched like that. Okay. It was not meant that this 2 has to have a 2. It was this 2 into this distance square, the x-axis distance square. Because the distance to y-axis is just the x coordinate. Assuming all these fellows were on the xy plane. They are on the xy plane. Okay. But as they rotate, they will no longer be on the xy plane. Okay. So then what will this answer be? So this is 80 plus 8 plus 27. Right? How much did you get? 115 kg meter square. And you can see very clearly that the moment of inertia about the z-axis is different from the moment of inertia about the y-axis. So first point, axis matters. Moment of inertia of this disk, we will later learn how to calculate it, about this axis is very different from the moment of inertia of this disk about this axis. That is, if the disk was doing this, the answer is different from if the disk is doing this. Depends on what the disk is doing. So if you just ask what is moment of inertia, no answer. What is moment of inertia about this axis for this object, there is an answer. I hope that part is clear. Okay, so now we have a simple formula for a single point particle. In fact, we have already used it. Now comes a case where we say, wait a minute, I would like to know what is it for a ring. What is a ring? A ring is a thin distribution. Right now let us assume I want it for a uniform ring. Actually I don't need it. It could be uniform, it could be non-uniform. Just a ring. Ring has, let us say, mass m and radius r. What will be the moment of inertia? How do you know it is mr square? Because this mass is distributed all over the place. Because if you took this little fellow, it is m1 into r square, m2 into r square, m3 into r square, and if you add it all up, you will get m1 r square plus m2 r square. Everybody has the same r. So therefore, this is equal to r square into m1 plus m2 plus m3 plus m4, which is just simply total mass m. So this is mr square. Do you see why it is mr square? Why? Because all of them are the same distance away. Why is this mr square? There is only one particle. So therefore it is mr square because its distance is r. This is not mr square because different particles are at different positions. But you can use mr square by just adding it up. It's a linear idea. I mean not linear, it's a summation idea. You can sum moment of inertia for this fellow plus that fellow will be the overall moment of inertia. Okay, it's a summative idea. So here if you look, this is the moment of inertia for a ring, and please notice I am not saying it is uniform. Need not be uniform. It could be very heavy here and much less density there. Center of mass will not be here. What will happen to the center of mass? It will move there. But moment of inertia about this axis, about O, with an axis like this, will be mr square. Later we will learn what to do when I have an axis like this, where this ring is rotating this way. Okay, there uniform will matter. For this, uniform doesn't matter. I hope that is clear. If I took a ring and I plonked some extra mass here, let us say this ring was mass m, and I threw a little bit more, let us say 2m, 5m and 3m here. What will be the moment of inertia of this entire system about this axis? Oh, it's all at the same distance r. So it is m plus 2m plus 5m plus 3m. So it is 11m into r square. So this will be 11m r square. I hope the idea is clear. So the basic concept is that all we need to look at is how far away each point particle is, as long as you can cut it up into point particles.